Hello everyone, I'm Chun-Wei. This is the part 3 video of the 3-6 quadcopter simulation control project. Today I'm going to introduce and demo the new mode, which is the path mode. Okay, so on my website you can see this new mode, and there are some information of this mode. So I will get into the demo, how to run this project. Okay. So after you download this project and unzip it, you will see some script. First, as usual, we will run the set drone control script. Okay. Okay. Next, we are going to generate the A matrix, which is the path matrix of the drone. Okay. So as you can see here, I use a simple sine and cosine function. So to give the drone a periodic path to move. Here you can see. So let's run it. After you run the script, you will see a matrix. Okay, so these are the position where the drones should go. Okay, X, Y, Z, X, Y, Z. And also the time step between each position is set to 0.1 second here. TSS 0.1 second. If you want the drone to move faster, you can set this TSS. And after we have the path for our drone to move, then we need to generate the exact X, Y, Z signal that will be inputted into the drone, the simulation model. Okay, so let's run this X, Y, Z signal path points.m script. You will find XCMD, YCMD, and ZCMD after you run this script. Okay. Here are also some information that you can see to know more about this script. Then we will open the simulation model. Here. So the XCMD, YCMD, ZMD, we just generated it. So later it will load it. Okay, let's just first run it. Okay, as it is running, I made some small changes here. Here you can directly control the yaw angle. And now I'm setting the yaw angle to always be a constant 0 so that it won't turn his head. Okay. Okay. Just wait a second. Alright, the simulation is done. Now we can go back to open this animation direct.m script to visualize the result. Okay, so I'm going to run this section, and I will bring up the simulation. Right, so you can see that the drone just follows and move as the path we just specified at the beginning. Okay. The difference between this mode and the previous one is that we directly select and design the path for the drone. It doesn't need a moving target to follow. So that is the demo. And here I want to mention the next point is, okay, how can we generate A? Which, in other words, how can we load our path into this simulation? By default, I use some mathematical algebra to generate the XYZ path. But in reality, if we have a really complicated path, for example, let's say if we have a complicated path like this. If we have this path, how can we load this path into the simulation? It can be done rather simple. So you just take each point, each section of it, okay, and extract the x, y, z data of each point. For example, this is x, this is y. Okay, so you can get every x, y, z of each section of the path, and you can store this x, y, z data into the A matrix, and you can make your drone to run or to fly in every complicated path you want it to move. Okay. So another point I'm going to mention in this video is about the controller. Okay, how I design the controller. Okay, so as you can see here is the controller. Okay, controller block, and the controller will take into some error, for example XYZ error and yaw error, also the order angles, its attitude, and its velocity, and some frame transformation information. So let's dive in to see the detail. Okay, so here in general you will see full controller, X controller, Y position controller, X position controller, and yaw controller. Okay, so in the Z controller, I use a P and D controller. Okay, so here is the P gain and this is the D gain, because now I feed into the velocity Z. Okay, so it is a PD controller. Also, because we know that if we want our drone to hover, it will need m times 9.8 force. Okay, so it is a PD controller combined with a feed forward loop here. And here I give it a reasonable thrust limitation, okay, in Newton. Okay, in Newton. What if we want to control the X and Y position of the drone? What should we do? Okay. Here I'll give you a simple example. So let's say this is the X direction, okay, and this is the Y direction. Now, if I want my drone to move in this direction, in X, what should the drone do? The drone should rotate in the Y axis, which means to pitch. Okay. So, to control the drone to move in X direction, the drones need to pitch. And to control the drone to move in its Y direction, the drone needs to roll. Okay. If you see the controller, X controller, we will feed in the theta angle, which is the pitch angle. If we want to control the Y position, we need to feed in the phi angle, which is the roll angle. Okay. And inside the controller, okay, give it a second. It is a outer and inner loop of the PD controller. The first PD controller will transform the Y position arrow and velocity to a reference phi angle. And the inner loop PD controller will transform the reference phi and the arrow of phi to the exact torque it needs. Okay. Same as the X controller. Okay, so in the X controller, it is the same. The first outer loop transforms the position to the angle, and the next controller transforms the angle to the torque. Okay, and here you can see that there are some PD controllers. It is because that if we want to have a good PD controller, we need to tune the gains, and it is really what requires a lot of time and effort. Also, if the model is a non-linear model, for example, like the 6-off quadcopter, whenever we change a single value of the gain, it will affect and change the entire behavior of the drone. So it's just a combination of gas, I guess. Okay. Let's look at the yaw controller now. So yaw controller, because what we feed into is already the yaw angle. So here we only need a single PD controller to transform the angle to the torque. Okay. Final, we talk about the realistic of this model, simulation model. So in this simulation model, we assume three things. First, we assume a perfect motor. Okay. Why? Because as you can see, there are no fluctuations for the motor output. So we assume a perfect motor. Second, we assume a perfect sensor, because if you see what we feed back, the signal we feed back, there are no noise. So we are assuming a perfect signal. Here. Third, we are assuming a perfect environment. So if you look into the environment block, there are no wind disturbance and any kind of noise to shake the drone. So we are assuming a perfect environment. Part 4 video, I will be introducing how to apply or add this kind of realistic elements into this model. So in the part 4 video, I'm going to show you how to model a drone with a wind disturbance. And using the same idea, you can add in the noise of the sensor, the fluctuation of the motor, okay, and any kind of noise you want. That's all. Thank you for watching this video. I appreciate your patience for me to update this project because currently I'm doing deep neural network controller and the fuzzy controller, and I will be uploading those videos maybe in the part 6 and part 7 series. Okay, again, thank you for watching. See you.